Hello, and once again, welcome to Eco Views and News. Very glad you could come along to continue our conversation on tipping points. We're going to look a little bit further into different kinds of tipping points. You may recall that last time we looked a little bit at what is in effect the ice albedo question, and the rates at which Arctic ice is melting is quite important, because one tipping point is thought to be related to the amount of reflectivity at either pole in reference to incoming sunlight. Beyond some point, as I indicated last time, the ice albedo feedback mechanism begins to operate, and the decline of Arctic ice is such that we can't, in effect, reverse the problem. The absorption of the sun at the surface is such that it keeps getting warmer and warmer, and having lost the ice, is no longer reflecting the sunlight back into space. On the contrary, it's absorbing it in both the oceans and in the land areas that are opened up from ice cover. So after some point, the decline of Arctic sea ice will become self-perpetuating. It's a positive feedback loop. As less sunlight is reflected back into space and more solar energy is absorbed in the darker oceans and land masses of the Arctic. Well, that's one tipping point, and we don't know where it is. We know the kind of positive feedback loops that can result from it, but who knows what's the crucial amount of Arctic ice that has to be maintained before that positive feedback loop kicks into effect. So that's one we looked at last time, Arctic sea ice, and changes in the Arctic sea ice thickness. The fact the thickness is getting, in fact, very much more diminished is worrisome, because it disappears much more quickly in the summer months. It doesn't come back and doesn't stay back as much as it could in the past. The second one that I wanted to look at a bit was this one of the melting, and I'm calling it /moving glaciers, because in effect they don't need to melt if they start moving from land masses into the ocean. They don't need to melt to have other effects. They can stay ice, but they're being displaced from land masses into the ocean, and in the process they're having an impact on sea levels. So it's that changes in sea levels from both the melting and the moving ice that we went over a bit last time, and we emphasized that both melting and moving were involved. I think the mechanisms of it were pretty clear. We illustrated how the ice melts, forming puddles on the surface, and some of those, in fact, drill down, in effect, deep holes into the base of the ice sheet. And that flow of water down those crevices, in effect, serves as a kind of layer along the bottom, which, in effect, lubricates the movement of whole blocks of ice. So it's not just glacial melt, but this glacial movement that's crucial. Especially when you see it toward the edges with the oceans and the continents, and whole blocks of ice can start to move off without melting. So this isn't a question of melting yet, but bang, you get glacial movement. And that combination, in effect, of glacial melt plus glacial movement is what's going to affect sea level on a global basis. Now, I wanted to look a little bit further into that to give you some sense of how massive it is and how quickly it's happening. It's occurring in Antarctica, it now seems, and that's worrisome in itself, because that's the biggest store of ice on the planet. But it's also occurring in the North Atlantic around Greenland, off of the glaciers that go into the sea there. And that's where it's been documented most dramatically recently. You may have seen some of the programs in popular science channels like the National Geographic channel. They actually had a program on National Geographic that dealt with this a while back. Back in 2007, they called it Glacier Meltdown, and they put it up and rebroadcast it every once in a while called Glacier Meltdown, and it's worth looking at it in some detail. If you get a chance to rent it from your local DVD store, or I think you can even buy the thing from National Geo. In any case, the school system should have it or acquire it to teach in science programs, because they talk, in effect, about the potential dangers of coastal flooding that emerge from this kind of circumstance. And I'll play a bit of an excerpt of it here just to give you a sense of how dramatic they make it. They talk about the coastal flooding as a major issue, and I think you'll agree that the way they've formulated it, it's actually quite dramatic. They're putting together basically footage from various storm surges, but it's a very important way to look at it as a potential problem for all coastal areas, not just ones that are close by. Let me try to capture it for you here.
The overwhelming power of nature. Floods, storms, rising sea levels. Climate change is already altering the face of our planet. Freak weather is no longer out of the ordinary. It's becoming the norm. Our planet's ice is melting, and that changes everything. Seas will rise, cities could be submerged, and millions may die.
There won't be any area near the coast that won't be hit hard.
It's inevitable that we're going to lose everything at the coast.
Now, that's a pretty dramatic statement for them to make, and I'd urge you to look into the science. Their facts are a bit dated now, from 2007. They couldn't be anything else. I mean, they're doing the best they can. Okay. Let me bring it up here.
Global warming. It's a term we hear all the time. But behind the familiar words is a frightening reality. Our planet is warming up, and the effect on Earth's ice caps is catastrophic. As temperatures go up, the ice is melting. Sea levels are beginning to rise. Around the world, ocean levels are increasing twice as fast as they were 150 years ago. In 2005, 77 cubic miles of ice from Greenland and Antarctica melted into the sea.
Now, that's not insignificant, right? 77 cubic miles of ice from Greenland and Antarctica. That's the two combined. But a cubic mile is enormous, right? It's a mile that way, a mile this way, and a mile straight up. 77 cubic miles melted into the ocean. That's a lot of transfer from land mass to the oceans. That's why they're pointing out you can expect sea level to rise. Just by comparison, they give you another figure.
For comparison, the city of Los Angeles uses about 1 cubic mile of fresh water per year. This is global meltdown. In 2001, scientists predicted that sea levels would rise by 3 feet by the end of the century. That's a big rise, enough to affect more than 100 million people worldwide. But now researchers like Bill McGuire, professor of geohazards, worry that the predictions might be wrong.
The official scenarios for sea level rise, if you like to call them that, were published in 2001, and they were based on research that was undertaken in the years running up to that, so they are completely up to date now.
Okay, well, that's very important to recognize. Bill McGuire here, who they interview here, is looking into this full time, and the point that he's making is that the sea level scenarios are based on data before 2001, published in 2001, collected before 2001, and they're completely out of date. He's saying in 2007. So by 2010, they're even more out of date. So get the sense of trend here, and look to the people that the experts are looking to for the measurements of these ice flows. They actually discuss in some detail, and we'll look at it here, how it is that they measure this kind of thing. It's actually very interesting and important to keep in focus here.
destroy a quarter of all the houses within 500 feet of America's coast. Recent research paints a more disturbing picture. Sea levels could rise as much as 20 feet by the end of the century. It's a bleak, even terrifying vision. But this is what scientists believe meltdown could do to us all. To understand what will happen when the ice melts, scientists need to study the processes driving the meltdown. Advanced modern technologies can reveal our planet's ancient history. By studying how things have changed in the past, they hope to predict our future. Sea level rise is nothing new. We know that in the ancient past, sea levels have been both higher and lower than they are today. It's a natural cycle, driven by the melting and freezing of the polar ice caps throughout Earth's 4.5 billion year history. When the ice caps melt, they release water into the ocean. When they freeze, they take it out again. Earth's climate alternates. There are ice ages when the temperature drops and the ice caps freeze and expand. And there are interglacial periods when the ice caps melt and release water back into the oceans. The cause of the cycle is the Earth's rotation around the sun. Earth's orbit around the sun varies in a number of complex ways. The most important is that it changes shape. It's not always a circle. Through a cycle lasting about 100,000 years, the orbit goes from being almost round to being stretched into an oval shape, then back again. In a more elliptical orbit, we travel millions of miles further away from the sun. Less sunlight reaches the Earth, and an ice age is born. Right now, our orbit is circular, not elliptical, and we're in a warmer interglacial period. But something is wrong. The ice is melting too fast. One of the places where that melting is running out of control is Greenland. Greenland, covering an area of 836,000 square miles, with ice of an average thickness of nearly 1.5 miles. Greenland contains 600,000 cubic miles of ice, and it's melting. Professor Conrad Steffen's job at the University of Colorado is to figure out what's wrong with the glaciers before it's too late.
We came first here on the Greenland ice sheet in 1990, where we set up a permanent camp on the ice. And the main objective was to measure the climate.
Each year, Steffen treks across Greenland, checking his remote weather stations. These beam data via satellite to his computers at Colorado. The news isn't good.
Okay, well, you get a sense of the depth of the study here. It's not someone going outside and putting their finger up and saying, gee, I think it's getting colder or getting warmer. And in fact, warming is not a new phenomenon. The procession and recession of ice sheets from glacial periods to interglacial periods, when they are pulled back to other glacial periods, is a regular phenomena in the Earth's celestial mechanics over the last million years or so. About every 10 or 12,000 years, there's a movement of these. At the last time the movement receded was about 12,000 years ago, but they come and go in 120,000 year cycles, sometimes 100,000 years. But they last longer and then retreat rapidly. Last longer, retreat rapidly. There's an asymmetry to the process. So the movement of the ice hasn't been a mystery for a long time. But what's troublesome now is those celestial mechanics having to do with the wobble of the Earth's axis and the distance from the sun, which was illustrated there in the clip, isn't accounting for the rapid warming that we're now experiencing and measuring. It's not just a model, these are measurements that have been made over decades. Now there's individuals out there from the University of Colorado since 1990 measuring the concept we discussed earlier, mass balance. The idea is the whole mass of the glacier is in balance. It's growing at the top where the snow is falling at the same time that it's losing mass at the edges. And it's doing that because of the mass balance. But when the mass balance is off, then you'll see that it's calving, that is creating icebergs faster than it's accumulating ice in the interior.
Glaciers gain as much ice as they lose. This natural balance keeps the ice cap stable and sea level rise in check. For the past 10,000 years, that's how it's been. Our ice caps have been stable. But now the balance is off. The edges of Greenland's glaciers are melting faster than the rest can grow. Greenland's losing 20% more mass than it gains from new snowfall each year.
If this continues, as the balance shows, they're losing more mass. And this is what we actually discovered. This is happening right now. They're losing currently about 50 cubic miles. Can this be sustained? No. If it continues like this, Greenland ice sheet will lose mass every year by a certain amount, and the sea level will rise.
To get a detailed study of what was going on, NASA installed a global positioning system to monitor the elevation of the glaciers and track their loss of volume. What they discovered blew them away. Glaciers were melting faster than ever before. They were literally sliding into the sea.
Well, you can see the problem as illustrated here and talked about by this gentleman from the University of Colorado is very dramatic. And in fact, it's been recently illustrated by a series of programs available in PBS. I don't know if you've followed these things, but there's a program called Extreme Ice that NOVA put out. And once again, you can actually view this one online. It's completely available for viewing online as a streamed video, but in addition, it's on a DVD, and I'd urge you to take a look at it. It actually has a trailer on YouTube, and you can get access to this now pretty easily. What's so dramatic about this is perhaps illustrated by its trailer. I'll play the trailer here a second to give you a sense of how fast these things are moving. And if we get a chance and have the time, we can look a bit at the DVD itself. But the trailer gives you a sense of time-lapse photography that will illustrate, in effect, how fast this is happening. Now, we usually think of something moving in glacial pace as slow, but if you take it in time-lapse camera, you see these things really as rivers of ice that are flowing very rapidly. And it's extraordinary footage. This is worth an hour's viewing on your DVD. Get it for your school. Get it at the local library. There's an awfully good chance they have it already. And they illustrate in great detail these huge blocks of ice that are calving off. That's the term they use, to calve off. But they're enormous. I mean, they're on the scale, well, you'll see they actually draw a picture of the nation's capital to give you a sense of how many times as big as the nation's capital it is as it moves from the land on into the ocean. Staggering information here. You get 3 miles by 3 miles wide by 1.5 miles thick, 1/2 a mile deep. That big in reference to the San Francisco Bay Bridge. There's the U.S. Capitol. Those are the masses of materials involved in the movement of that ice in just 1 hour and 15 minutes, basically, 75-minute period. Take a look at it. It's called Extreme Ice, and it's certainly worth viewing to get a sense of the rapidity of this. And also, beyond moving glaciers and melting glaciers, we'll want to talk next time about other forms of destabilized methane and what that means for the community as well as ocean currents. Ocean currents are another kind of destabilizing process that we'll talk about in reference to the North Atlantic. In particular, the Gulf Stream could be knocked out of kilter, and the whole